for me. I've only done airborne field work, which is very different than being on a ship, and where it's just very isolated. Like, that ship is really your whole world, and all those people on the ship are your whole world. And then outside the ship is this just very hostile landscape. It's cold, there's polar bears, there's water that can open up underneath your feet. And so it was a very interesting experience to be on the ship, which was very safe and warm and felt good. But then we'd go out and we'd do our field work, and we'd set things up, and we'd be out on the ice, and you could feel like this is a very wild environment. As we were transiting through the ice, we were searching for a suitable ice flow, something that was thick enough that could support us working on safely and also survive throughout the year. While searching for that flow, we had different satellite tools that we were using that would identify the shape of the flows. We could see how big the flows were, but what we didn't know was how thick they were. We went to some of these flows and we found, though these are really thin, we can't actually use this flow. We looked at some ISAT-2 tracks in hopes that some of the flows that we had identified, we could see how thick they were. It didn't work out this time, but for a future expedition, I think we've identified ways that we could utilize ISAT-2 or something like ISAT-2.
While there wasn't enough ISAT-2 data for MOSAIC or the Multidisciplinary Drifting Observatory for the study of the Arctic climate to use, Dr. Nathan Kurtz and the team were able to locate an area with the right amount of sea ice thickness by using different methods. Likewise, scientists often use various methods to measure other aspects of our planet, like forests. So, why take measurements of the same thing using different methods? And how does measuring sea ice thickness relate to tree height? Let's take a closer look at the Ice, Cloud, and Land Elevation Satellite, or ISAT-2. Its main purpose is to measure ice thickness using its sole instrument, ATLAS. But it also measures tree heights as it orbits Earth. This is done with photon-counting lasers and algorithms developed to differentiate what environments they are measuring. An algorithm is a step-by-step procedure for solving a problem, usually a mathematical one, in a limited number of steps. Claudia Carabajo was the deputy lead for the Flight Science Receiver algorithms, one of many subsystems of the ATLAS instrument.
The algorithms that process the data on the ground for ISAT-2 are tailored directly to address that characteristics of the surface. So they are tailored to sea ice and vegetation. The coherence of those photons when reaching those surfaces changes, so the algorithms need to be specifically tailored to the surface type. Of course, comparisons against other data sets help you, and sometimes you need the help of an additional data set as you're processing.
When I was on MOSAIC, we took specific measurements that are useful and will be used. By combining multiple measurements together, we're able to quantify and see whether ISAT-2 is making its measurements accurately and how it's needed to be done.
One of the ways that you can actually figure out if ISAT-2 is actually measuring the right thing is to compare it with observations that are being collected by other means. For example, airborne campaigns, other satellite data, and see what the surface looks like. You can look at how things are changing at different seasons.
Whether it's sea ice thickness or tree height, comparing data collected by different missions and field campaigns allows scientists to better understand how the instrument works. Dr. Laura Duncanson uses LiDAR data to create 3D maps of forests, and Dr. Nancy Glenn is currently looking at various ways in which tree height data collected by ISAT-2 and GLOBE observers can be utilized. For both, tree height data adds to our understanding of Earth's systems.
Of course, we can't go out into the woods all over the planet and measure every single tree on the ground. So for ISAT-2, these estimates of tree height, we don't know exactly how precise they are or how good they are in all of the different forests around the globe. There's a lot of variability in forests.
Just like how taking field observations and airborne data collected of sea ice thickness can act as supplementary data to ICESat-2, tree height measurements collected in the field can also be used to do the same. This supplementary data can help scientists account for variability between different environments when looking at measurements collected by satellites. As mentioned, tree height measurements can be taken in different ways. One method is to use trigonometry to estimate the height of a tree. This is the method that students and citizen scientists use. By measuring the distance to the tree, along with angles A and B, using a handheld clinometer or the one built into a smartphone, observers can calculate the height.
Having people go into the woods and actually measure tree height to compare to the satellite estimates of tree height gives us a sense of how reliable those tree height estimates are, and maybe some ecosystems that they're particularly good at doing tree height or particularly challenged at doing tree height.
Now we know that by taking measurements of the same thing, using different methods can help scientists. Taking tree height measurements adds a whole new data set for satellites and instruments such as ICESat-2 and JEDI to compare with. These measurements also provide content that only an observer on the ground can provide, like recent changes including drought, fire, invasive species, and more. Now that leaves the question, why do scientists study trees?
So for decades now, we've had really good maps of where there are forests and where there aren't forests, but we've never before known how tall the trees in those forests are. And this is a really critical piece of information because it tells us not only, of course, how tall the forests are, but how much above ground woody carbon they store. Forests represent one of the biggest carbon stocks on the Earth's surface. And if we cut down and burn forests, we essentially are pushing more carbon into the atmosphere. And if we allow those forests to regrow, we're sucking that carbon out of the atmosphere. But we don't know right now how much carbon is where in Earth's forests because we've never had that third-dimensional measurement of Earth's forests, which is so tightly linked to its carbon content.
Using tree height not only helps scientists track how much carbon is getting released into the air, but can also be used in other ways.
Tree height is really important for us is that we're interested in knowing how tree height is affected by increased CO2 or increased temperatures or decreased temperatures. And that gives us an indicator for making predictions about trees in the future. What we're interested in is that trees and the differences in tree heights provide some level of what we call structural diversity. And structural diversity can be really, really important for a health of an ecosystem, as well as provide habitat for a variety of different types of animals. So we're using NASA resources, NASA airborne data, as well as satellite-based data like ICESat.
Many Earth-observing satellites, such as Landsat, can only see a top-down view of Earth. This information comes in the form of two-dimensional images made up of pixels between the size of 30 meters squared to 500 meters squared. But now, with JEDI on board the International Space Station and the launch of the ICESat-2 satellite in 2018, scientists are able to see height added to this top-down view of Earth. By taking and submitting tree height observations, citizen scientists and students can help scientists and researchers, not just by providing measurements from different ecosystems, but by providing a different type of data. What seems like such a small piece to contribute can help scientists across the world.
The Globe Observer tree observations essentially let people all over the world measure tree heights and give us that information where we can't go into every single forest ourselves as a small group of scientists.
From a scientist's perspective, but also somebody that participates in citizen science, it's a great intersection. More data, the better. But also the connection, right, is that the connection between scientists and the community, and scientists understanding what's important to our communities and being able to engage and learn from one another.
There is a large part of collaboration between the instrument scientists and everybody working on every aspect of the Atlas instrument, and the mission scientist and his deputy and everyone else in all the universities. Citizen science is really important to get the community involved. It motivates everybody to be more informed about the science and also perhaps motivate a crowd of new scientists.
All of this is important because one, it's the pursuit of answering questions about our natural environment. Our natural environment is changing very rapidly.
A tree height measurement that's taken by citizen scientists could be useful for us.
It's really important for us to monitor what is here now so we can document that, but also use that in models to predict what might be here in the future.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.